telescopes. So what are telescopes? What do they look like? What are the different kinds of telescopes? This is a telescope, that's why I brought it here. If we're lucky and it's sunny next week, we'll get to use it. So that'll be something to look forward to, but it's easy if we have a telescope to get an idea of what a telescope does. So the first thing of a telescope is it's a bucket. Now my telescope here, I think, literally looks like a giant bucket. It's hard to even tell it is a telescope if you don't know what you're looking for. But the key elements are, well, it has a large aperture. So the size of this opening is how much light that the telescope can gather, which is an important part of how the telescope works because it can allow us to get more light from a given object by collecting it and focusing it to a point. The second aspect of a telescope is it can let us sort of zoom in on things. It can magnify, it can clear our vision. So unfortunately for the astronomers, fortunately for all of us, we're under an atmosphere, and that limits how much a telescope can improve our vision. But if you look at this guy, this has all the basic elements of a telescope, because it is a telescope. So if you look down in there, you'll see there's a mirror. I guess, can you see at the bottom? Everyone can come up here later. So it's not just a bucket, it's a bucket with a mirror in the bottom, okay? And that mirror is slightly curved. Let's see if we have a picture. So we have two types of telescopes. One uses a lens to focus light to a point. That's called a refractor. And this one is a reflector. So, so that mirror down at the bottom is this mirror here on the right of our reflector. Now, almost all, or maybe all, telescopes that are used professionally nowadays are reflectors, okay? And the reason is we want to make the telescope big. And to make a big, if we had a refractor, we need a lens this big, and we need to hold it and make sure it didn't change its shape as we pointed at different parts of the sky. And you can imagine a big piece of clear glass like that, it gets heavy, and you have to hold it there, and also it's going to sag under its own weight, and it can be expensive. On the other hand, the mirror at the bottom, sure it gets heavy, but it's down at the bottom of the telescope usually, and we can put a lot of support behind it because the light doesn't pass through it. We don't have to support it just on the edge, we can support it from behind. So this telescope is a reflecting telescope, not a refractor. So if we look at what the light does in the refractor, it comes in the front through a lens, it gets focused, you'll have a second lens. That second lens is needed for us to see through the telescope with our eye. If I wanted to put in a piece of film, I don't need this lens. I could just put a piece of film around here and detect the radiation that way. The lens allows us to look through it. So this telescope is like the one on the right. So you can see the elements, right? So we have a mirror at the bottom who's slightly curved. Then there's a mirror here, right? Which is the same in that picture. This mirror is flat. You can see it, it's in the top. That mirror is there to direct the light out to the side. Now, why would we need to do that? Why do you think? Well, if I stood here, I would be blocking my view, right? So, big telescopes, much bigger than this one, will actually have an instrument right here in front of the mirror. And that's called the prime focus. And if the telescope were like 4 meters across, you can imagine it wouldn't be hard to sit there, because you could have a little cage that was 1 meter in diameter and sit there. my little telescope, if I stand in front, guess what? I'm blocked. So then this mirror directs it out to the side. So the one there is on the right is called a Newtonian reflecting telescope. Now generally how they work nowadays is they'll either have something here or this mirror here. There'll be a mirror here in the middle that is not tilted but horizontal. And that will direct the light back that way through a hole in the middle of that lower mirror. And then you put the instruments not way up here, but back here, near the ground, where it's easy. They can get heavy, and it's easier to support them there than to support a huge weight up at the top. So that where it's, so there's the different types. So the prime focus, you would be sitting here with your detector. The Newtonian focus is what you see in this telescope, which is quite convenient for me to look through there, because this is at my height. The professional telescope usually has the focus down below, and you put your instruments down at the bottom. So the Hubble Space Telescope looks like the one on the right, except it's big, right? It's 2 meters across about on the bottom, where this is just 30 centimeters. There are other tricks that you can do, like this thing at the bottom is a curved surface, but you could make the second one curved too. And that's sort of like putting better and better optics. Like people might have, you have a little, your little camera on your phone might have one lens or two, but if you buy an SLR camera, it has a bunch of lenses, and that means that the pictures are clearer and clearer. The same with the telescope. We need at least one curved surface, a mirror or a lens. We need at least one. But if we have more and more, we can make the picture clearer and clearer over a larger and larger region of sky. Okay? So this one's really basic, right? I have one curved surface. I have a bunch of lenses here in my eyepiece, but that's mainly for my comfort. So if we think about what are the different things that we could do with our telescope to make it better or worse, one is we could make it bigger or smaller. So that affects the sensitivity of the telescope. So here is a picture of the Andromeda Galaxy with a small diameter of telescope. Your eye is really small. So with your eye, you can see this part of Andromeda here, this fuzzy bit you'll perceive with your eye. Now if we increase the diameter of the telescope, well, we get something a lot better, right? So we can make out fainter details in that image. So that's why we like to build bigger and bigger telescopes. So the largest telescope on Earth now is 12 meters across. They're planning here at UBC, among other places, to build one that's 30 meters across. Now, if you think about it, even 12 meters doesn't really fit in this room. So they're thinking of 30 meters, which is sort of like the mirror is comparable to the size of this building. So huge. So the reason we build larger diameter telescopes is that they're more sensitive. There's more light coming in here to our focus, so we can see fainter and fainter objects. Now the second thing that we can think about for making a bigger and bigger telescope is how clear is the image? What's the angular resolution? If we have two objects that are close together, can we separate them? So at the top, we're just looking, we have two objects, and eventually they become so close that you can't distinguish them apart. And these rings that are seeing has to do with the fact that light is a wave. So when I take light and I make it go through this region, even if the light is coming from one point, what it will look like on my detector or whatever will look like those things with the rings. Okay? Now, we did this experiment ourselves in class. We squeezed the light between our fingers, and you can see these fringes. Our fingers are millimeter apart. The telescope is huge, but it will still exhibit these fringes. And once you see those fringes, it becomes harder and harder to tell things apart, that they're in different places. Okay? Now, if there were no atmosphere, the size of these fringes, or the resolution, is, that's a 0.25 times 10 to the 6, lambda over d, where lambda is the wavelength, and d is the diameter. So if you remember, when we were talking about our experiment with our fingers, lambda over d was about 1 in 1,000. It was about 1 in 1,000. Lambda was 1,000th of d, so if we were to multiply that through, that would be 0.25 times 10 to the 3 arc seconds. 250 arc seconds, I guess. Which is a little bit, it's a few arc minutes, right? 200. And that's what we were guesstimating. That was a few arc minutes were those fringes. Now, when we make a telescope like this guy, let's see what happens, right? Let's imagine this is 30 centimeters across. Let's call it 40 centimeters across to make the math easy. So that's 0.4 meters. That's d on the bottom. Lambda is maybe 0.4 microns, 0.4 millionths of a meter. So that number there is going to be 0.4 millionths divided by 0.4. That's why I chose those. So it's just 1 part per million. So this telescope, if we were to point it at the sky with no atmosphere, would have an angular resolution of 1/4 of an arc second. That's pretty good, except we have an atmosphere. So our atmosphere jiggles up the light that we see through it. And you can see that. Like when you look at a star, what do stars do when you look at them in the sky? How do you know it's a star versus a plane? Or a star versus a planet? They flicker. And that flickering, that twinkling, is because of the atmosphere being turbulent. You can see it with your eye. And the scale over which things jump around is about an arc second. And that what you're seeing with your eye is things getting magnified and demagnified and stuff like that, because you can't resolve it that small. But it's about an arc second, is that scale of the flickering. That's why a planet doesn't twinkle, because it's big. It's many arc seconds. But that's the problem, right? So I built this. This telescope has an angular resolution of 1/4 of an arc second, but the sky keeps me from achieving that. When I look through it, especially down here at sea level, the images might be 2 arc seconds, right? So, because there's lots of atmosphere above. So what we need to do is we want to find ways to mitigate that. Now, if you are not observing in the visible, but in the radio, the atmosphere doesn't have that effect, so you can get higher resolution. But if you think about in the radio, lambda, instead of being less than 1/millionth of a meter, is like 1/10th of a meter. So to get the same resolution, your telescope has to be 1,000,000 times bigger. Right? Because the wavelength is 1,000,000 times larger, maybe. You see what I mean? The wavelength is 1,000,000 times larger. The lambda, the d, has to be 1,000,000 times larger. So my little baby telescope, 1/4 of an arc second, with 40 centimeters, if I wanted to have it be a radio telescope, instead of 0.4 meters, it would have to be, 400 kilometers across. You see how that works? So as we go to smaller wavelength, for a given size, we can get finer angular resolution. We can build radio telescopes even thousands of kilometers in size, by having an antenna on different parts of the Earth and combining the signals in clever ways. So we can get this very high angular resolution, even in the radio, because we can make a really big telescope. So here's what Andromeda looks like with different angular resolutions. So 1 arc minute is sort of around your eye. Look what it looks, it's 10 arc minutes. Not so great, not so great. 5 arc seconds and 1 arc second, it's perhaps hard to tell from our picture, but maybe one thing that you can look at is if you look at sort of faint objects in here, they're fuzzier than over here, and you can tell if they're sharper, it's easier to pick them out. Right? So we like to have high angular resolution, not only because it makes for a prettier picture, but it also means we can see fainter and fainter objects out there in the sky, that higher angular resolution. So this telescope through the atmosphere is similar to the last picture, where on the lower right. So that's the angular resolution. So this is your worksheet, but we'll come back to it because I want to just get through. We'll do a little bit more background with the worksheet first. I'm going to turn on the lights. So this is like the graph that you see in your worksheet. It just indicates, just so you can interpret, what radiation reaches the surface of the Earth. If you're in a mountain, or you can see there's that airplane, we put telescopes on airplanes. There it's to look at infrared radiation. But things that are outside of the visible band and the radio generally do not reach the surface of the Earth. A little bit of ultraviolet light does reach the surface of the Earth. So we'll get to the worksheet in a second. So how do we collect and process our data? We use telescopes. They'll have different, this basic idea, we can stick this in space, have it focus X-rays. We can have it on the ground if we're limiting ourselves to radio waves and visible photons. So an X-ray telescope or a radio telescope will look similar to this, but there'll be differences. Gamma rays, we can't focus them. We don't have a way to focus gamma rays. So gamma ray telescope works quite a bit differently. Gamma rays come in to some material, they interact with that material, maybe make some antimatter, believe it or not, and we detect that antimatter that's produced. So that's how a gamma ray telescope would work. But we also have telescopes that measure things other than light, right? So now we have telescopes that detect neutrinos, but they're in quotes, because the telescope really has to do with light, basically. But we have telescopes that detect neutrinos. We have telescopes that detect gravitational radiation as well. So these are the different things. And you can learn more about it on the website.